Hello everyone. We start the sixth session of Advanced Thermodynamics. We continue the subject according to yesterday session. We continue and solve other problem. In this problem, consider that an air compressor in a gas station take a flow from ambient air at 100 kilopascal and 290 Kelvin and compress it to 1000 kilopascal in a reversible adiabatic process. So we want to know the specific work required and the exit air temperature. A specific work means work per kilogram. So what we have, air compressor is a control volume with single inlet and single outlet. According to problem, this process is adiabatic, so rate of heat transfer is equal to 0. We have continuity equation. It means that mass flow rate at inlet equal to mass flow rate at outlet. First law of thermodynamics means mass flow rate cross enthalpy at inlet equal to mass flow rate enthalpy at outlet plus rate of work. This is the first law of thermodynamics. Good morning. And we also have second law of thermodynamics. Because of reversible and adiabatic process according to assumption of problem, so the process is isentropic, means rate of entropy generation equal to 0. So entropy generation is 0. So according to constant CP K, we consider isentropic process for temperature means T temperature at exit equal to temperature at inlet cross relative pressure at outlet divided by pressure at inlet, power law, power 2 K منهای 1 K minus 1 divided by K. So if we compute this, we see that the exit temperature equal to 559.9 Kelvin and work of compressor equal to enthalpy at inlet minus enthalpy at outlet equal to Cp sef cross T at inlet minus T at outlet. That is equal to minus 271 kilojoule per kilogram. So minus work show that energy put into the system. So the environment needs work down on the system to compress the air. For example, you should connect compressor to electricity or other things that can prepare this work for the compressor. Any question? Okay, we continue. Okay, consider transient process. The process that we investigated before this section, we consider a steady state process. Means that rate of time for every quantity equal to 0. But in transient process, rate of time is not equal to 0 because variation occurs in the control volume. For example, for the second law of thermodynamics, rate of entropy of control volume, that is mass of the control volume cross entropy of control volume, equal to addition of rate of mass flow rate, mass flow rate cross entropy as inlet for all the inlets or one inlet, minus addition of mass flow rate at exit cross entropy as exit, plus addition of rate of heat transfer to control volume divided by T plus entropy generation. So in transient process, we can integral between initial time that considers 0 and reference time or consider time at T. So the differential with T mass cross entropy differential dt equal to m2 s2 minus m1 s1 for control volume. This is the left hand side of the equation 7.11. So integral of right term first, the first term on the right, integral of between 0 and t summation of mass flow rate cross entropy at inlet differential dt equal to sigma or summation of mass flow I cross entropy at I. It means that it may be we have more than one inlet. And the second term, integral of between 0 and t summation of mass flow rate at exit cross entropy differential dt differential t is equal to summation of MESE, means that when the mass going out of one outlet, entropy decrease due to exit. And the last term, integral of S rate of entropy generation equal to entropy mean between state 1 and 2. So the above equation for transient process convert to below equation. So m2s2 minus m1s1 for control volume equal to summation of MISI minus summation of MESE plus integral of summation rate of heat transfer divided by T differential dt and plus entropy generation between initial state 1 and final state 2. So if we consider rate of heat transfer is constant and uniform from the system, this integral convert to integral of between 0 and t rate of heat transfer divided by T differential dt. So the final form of second law of thermodynamics for transient process is according to equation 7.13. Okay, this is equation. Now we want to solve a problem for application of this equation. Any question? Good morning, everyone. Jabbar, Kazem, Maki. Any question? Okay. Okay, we continue and solve an example. Consider to this example. Assume that air tank has 40 liter of 100 kilopascal air at ambient temperature 17 centigrade. The adiabatic and reversible compressor it start to charge the tank to a pressure of 1000 kilopascal, and then it shut off. We want to know how hot air in the tank gets and the total amount of work required to fill the tank. So consider a simple example. We have a tank. The first state of a tank, the volume of a tank is 40 liter. And initial state means state 1 of the system is 100 kilopascal pressure and 17 centigrade temperature. Okay, we use a compressor and increase the pressure of inside air tank to 1000 kilopascal. We want to know two things: temperature of air at state 2 after increasing pressure and total amount of work required for the fill the tank. So this is a transient process. Why? Because we have a tank, it has initial pressure 100 kilopascal. This tank connect to compressor. So compressor put mass into the system, increase the mass of the system with increasing pressure to 1000 kilopascal. So when we pressure of the chamber or tank reach to 1000 kilopascal, it shut off. So it's a transient process that we have inlet that air enters to the system. So if we want to solve a problem, we have several things. First, continuity equation. M2 minus M1 equal to M in means that variation of mass of tank is dependent on mass of inlet, mass of the compressor. The other equation is energy equation, first law, means M2U2 minus M1U1 means variation of internal energy of control volume or tank equal to heat transfer between state 1 and 2 minus work done between state 1 and 2 plus M in H in means mass of the inlet air and cross enthalpy of air. And the other things is second law of thermodynamics, means M2S2 minus M1S1 equal to integral differential Q divided by T plus entropy generation between state 1 and 2 plus mass of inlet temperature cross entropy at inlet temperature. So according to assumption of the problem, the compressor is adiabatic and reversible. So due to adiabatic process, Q between state 1 and state 2 is 0. So process is reversible. So entropy between state 1 and 2 is 0. So entropy at state 1, entropy generation is 0. So M2S2 equal to M1S1 plus M in dot S in. For M in, we use M2 according to continuity equation. So entropy between state 1 and 2 is the same. So according to ideal gas law, we compute the entropy at state 2 from table R.7. We can compute temperature and internal energy. According to ideal gas law, we can compute the mass of the air at initial state 1 and final state 2. So easily we can compute the work between state 1 and 2. That is equal minus 31.9 kilojoule. So this is a amount of work required to fill the tank. Also the temperature is determined T at temperature at state 2 equal to 555.7 Kelvin. This is example of transient process. Any question? Okay. We are going to solve other problem. So this problem is calculate the work per kilogram to pump water isentropically from 100 kilopascal and 30 centigrade to 5 megapascal. So this water pump considers a process steady state, reversible, and adiabatic. Why reversible and adiabatic? Due to isentropically of water pump. So we neglect the changing kinetic energy and potential energy. So the energy equation, so we have only one inlet and one outlet. So mass flow rate at initial m1 m dot 1 equal to m dot 2. The energy equation is first law, means enthalpy at inlet equal to enthalpy at outlet plus a specific work. The second law, according to isentropic process, means SE minus SI equal to 0. So if we want to use this, we can back to this equation. For a steady state process in a reversible with no changes in kinetic and potential energy, and also adiabatic process, the work can be computed from this integral. Work equal to minus integral between state I and to E, a specific volume cross differential dAp. So we use this equation to solve the problem. We consider two constant specific volume of water due to incompressibility of water liquid. So we consider a specific volume nu is equal to this value and don't vary it during process. So nu is constant, the work equal to a specific volume cross pressure at exit minus pressure at inlet, that is equal to 4 minus 92 kilojoule per kilogram. Any question? Yes, Abdul Sadat, you should use table. But why I can't show the table to you? Because it is basic thermodynamics. You should review thermodynamics yourself and we continue the lesson. Volume is not fixed in this problem. Jabbar is not, volume is not constant. A specific volume is constant because of incompressibility of water liquid. Incompressibility means density or a specific volume doesn't vary during this process. All the liquid are incompressible. It means that density or a specific volume is constant. Other question? Okay, other question? Okay, Kazem, the process is isentropic, not entropic. It's not an operation, it's a kind of process. Okay, isentropic process means that reversible and adiabatic process between state 1 and state 2. Any other question? Okay, we solve other examples. Okay. Okay, consider to this example. Saturated vapor, kind of saturated vapor means R410A kind of refrigerant enter the uninsulated compressor of a central air conditioning system at 5 centigrade. So the compressor is not isolated. So we have heat transfer from the compressor to environment. The flow rate of refrigerant through the compressor is 0.08 kilogram per second. Mass flow rate of air through the mass flow rate of refrigerant. And the electrical input power is 3 kilowatt. The exit state of compressor is 65 centigrade with 3000 kilopascal. Any heat transfer from the compressor is within the ambient environment at 330 centigrade. Determine the rate of entropy generation for this process. So this is a steady state process, single input and single output. We also assume negligible changes in kinetic and potential energy. So what we have, a continuity equation means mass flow rate at inlet equal to mass flow rate at exit. The first law of thermodynamics means rate of heat transfer plus mass flow rate cross enthalpy at inlet minus mass flow rate cross enthalpy at exit minus rate of work of control volume. This is the first law of thermodynamics. And also we have second law of thermodynamics. It means that mass flow rate cross SI minus SE means variation of entropy between state I, inlet and exit, plus rate of heat transfer divided by T0 means environment temperature plus entropy generation. So for refrigerants 410A, we can use table B.4. So for a state saturated vapor of 5 centigrade, we can use table B.4. Enthalpy at inlet and entropy at inlet can be read from the table. At final state means 65 centigrade and 3000 kilopascal. So enthalpy at exit and entropy at exit can be computed from this table. So from an energy equation, we can easily compute this. So mass flow rate is 0.08. You can see it in this example. Cross enthalpy at exit is equal to 307.8 minus at enthalpy at inlet 280.6 minus rate of heat transfer according to problem work of electrical work of compressor means 3 kilowatt. So minus 3, that's equal to minus 0.824 kilowatt. This is the rate of heat transfer from compressor to environment. The other is entropy generation from the second law of thermodynamics. Entropy generation equal to m dot rate of mass flow rate SE minus SI minus rate of heat transfer divided by T0. So if we use this, mass flow rate equal to 0.08 cross entropy at exit according to above value of the table and entropy at inlet according to above table minus rate of heat transfer, that is minus 0.824 divided by temperature of environment, that is 30 centigrade, that is equal to 303.2 Kelvin. That's equal to finally equal to plus 0.00166 kilowatts Kelvin. This is the entropy generation of compressor. Any question? Okay. خب question. The compressor loses 1 point of heat to surrounding and entropy generation is 1 point. No, entropy generation is uh, point 0.00166 kilowatt Kelvin. Okay, remember that you point to wrong number, Jabbar. Oh, Kazem, why the value of entropy is very small? Because it's per Kelvin. Consider, Jabbar, consider, Kazem, it's according to its equation equal to 0.1 kilowatt per Kelvin. So if you want to know the actual dissipation, you should cross this entropy generation to temperature of environment. So it's go up to a more value for the heat transfer and dissipation. We also, you know, also that the main subject of advanced thermodynamics is exergy. We start this subject next session. Okay, next session we talk about the exergy and you know more about the entropy generation. We consider to this there. Okay, any question? Okay, that's enough for today. If you have any question, ask it please, or if you don't have any question, we can close the session until the next time. You remember that I will send you homework in LMS. So you do it and upload it in LMS. Okay, today or tomorrow I will send you 2 or 3 problem to solve at the weekend and send me at the LMS site. Okay, yes, for thermodynamics you should upload the answer in LMS, not Ballet group. Okay, okay, if you don't have any question, we can close the session. Be successful. Bye until next time.